Albedo feedback is a obvious positive feedback system in the Earth system. The way the Ice-Albedo feedback works is we can consider our planet here, and this is not Earth, but this is a planet that's very similar to Earth. It has ice at both of the poles, and the ice has a very high albedo, meaning that solar radiation that tries to approach the Earth, or not the Earth, this is not the Earth, remember, this is a different planet, but solar radiation that approaches this planet, if it reaches the surface near in the tropics or mid-latitudes, and it reaches a dark surface, that radiation will be absorbed, and that radiation then will be used to heat up the planet. By contrast, if that radiation reaches the poles where the ice exists, the radiation will then be reflected back out to space, meaning that very little radiation will actually be absorbed, and thereby the Earth will not heat up. So we can think about this ice-albedo feedback as a coupled system where it involves three different parameters. The parameters are global temperature, and global temperature is going to control the extent of ice sheet coverage, and ice sheet coverage is going to control the albedo of the planet. Okay, and obviously as the planet has a higher albedo, what that's going to mean is that less of that radiation is actually going to be absorbed by the planet, and that's then going to modify the global temperature. So what we're going to try to draw here is how this feedback loop actually works. And we'll start by basically connecting these different components of global temperature, ice extent, and albedo together in a way that makes logical sense. So we know that as global temperature increases, that is going to modify the extent of the ice sheets. Right? So as global temperature increases, what we might actually expect is that we are probably going to start melting the periphery of these ice sheets just a bit. So we could go through and we could imagine that our ice sheets are going to retreat just a little bit, right along the edges of the ice sheets. Okay, and as those ice sheets melt away, what's going to be in their place is land. So we might imagine that as temperatures increase, ice extent is going to decrease. Okay, it might just be incremental change in albedo. Okay, so increases in global temperature would lead to a decrease in ice extent, and I'm going to denote this by an open circle, which is indicating a negative coupling between global temperature and ice extent. What that basically means is that as global temperatures go up, ice extent goes down. Okay, so they're going in the opposite direction. And we could use the same rule: as global temperatures go down, ice extent would go up. So they're going in opposite directions, and therefore it's a negative coupling. As ice extent changes, that of course changes albedo. So in our example here that we showed in our diagram, we saw that as we decreased ice extent, we got rid of the high albedo portion of the land surface, and then overall, globally, this results in a decrease in global albedo. So, a decrease in ice extent results in a decrease in albedo. So, they're going in the same direction, right? If ice extent increases, albedo increases. If ice extent decreases, albedo decreases. And I'm going to represent this by a filled circle, indicating a positive coupling. Our feedback loop is almost complete. We just need to connect how changes in albedo influence global temperature. And if we're just thinking about the shortwave component of the surface energy budget, what we know is that as albedo increases, or in this case, let's keep it consistent here. As albedo decreases, like we're showing here, more solar radiation is going to be absorbed by the Earth system, and therefore, as more solar radiation is absorbed with a decreasing albedo, that's going to result in an increase in global temperature. So we're going to draw a connection between albedo and global temperature, and let's recall here what sort of direction this coupling works in. If I decrease albedo, like we're shown here, that's going to increase the global temperature. If we were to increase albedo, that will decrease the global temperature. So it's a negative coupling. We'll again represent that by a filled circle. Okay. And overall, what we can see is that what we have is a negative coupling between global temperature and ice extent, a positive coupling between ice extent and albedo, and then a negative coupling between albedo and global temperature. When we went through this example here, we started off with a planet that had a certain amount of ice extent. We then caused some sort of warming. It doesn't really matter how that warming occurred. The fact is we had warming. As that warming occurred, we decreased ice extent. That resulted in a decrease in albedo. And as we decrease the albedo, what now happens is that the Earth Planet X becomes warmer. And so as Planet X becomes warmer, what's going to happen next is that you're going to melt some more ice sheet, some more of the ice sheet. Okay? And if you melt more of the ice sheet, you're going to further decrease the albedo. That's going to result in more warming. So the system that I've drawn here has two negative couplings and one positive coupling, and collectively it ends up being a positive feedback loop. Okay, and the way this works is that we have two negative couplings. That's like multiplying two negative numbers by each other, and what you get out of that is a positive feedback loop. So this sort of feedback loop is positive in the sense that it's going to want to accelerate the change.